this architecture, we can only do 1 and 2 qubit measurements. We can't do a 3 qubit measurement or something like that. So that's why I've drawn it like this. And I mean, this isn't the only way that I could have drawn it. This could have gone first and this could have gone second. I don't know. I mean, I'm sure you can make it work in any way. Well, I'm not sure, but probably. We can see what happens anyway. So what should I do here? Let's vote. So for here, should it be Z tensor Z? Or should it be X tensor X? Or it could be some fancy combination, but these are the simplest measurements. Okay, so how many votes for Z tensor Z? Well, so which should we try? So there's an issue here. So we already know what Z2 is, right? Z2 is it's a +1 eigenstate of Z2 because we know it's in ket 0. So if we measure Z1, Z2, which is this, and Z1, Z2, we already know what Z2 is. That would tell us what Z1 is. And that's bad because we don't want to learn Z1. That would collapse the first logical qubit. We'd be measuring the first logical qubit, which we don't want to do. So this is a bad idea. But X tensor X is okay because X tensor X, it anti-commutes with one of the stabilizers. Which means it's not going to destroy any, when you measure something that anti-commutes with a stabilizer, the outcomes are going to be 50-50. You don't learn anything about the encoded data, about the logical data. So these qubits are not affected because it anti-commutes with this. So let's try this. First we measure x1, x2. Okay, so that's here. Like that. All right, so x1, x2, it anti-commutes with this guy, so we throw away that. You replace it with plus or minus xxi. Okay, it commutes with logical x1, so that stays the same. So it would anti-commute with this, so I multiply by the stabilizer, so it commutes. So I get zzi, so this is logical x1, logical z1, and it commutes with these guys. So that's what's happened so far. So essentially what we've done is we've sort of moved the information, some of the information into the second qubit. We've entangled them in some interesting way. Not that interesting, but we've started to entangle them. All right, so, and actually, yeah, okay, so now what should I do? Let's see. We're up to here now. So I want to measure these two, I think. So for example, I don't want to measure XX again. Because XX, if you look at this, X1, it's equal to XII, which up to this would be, so let me make this a force measurement. So I'll put a +1 there. So if you happen to get a -1, what you should do is you should multiply by IZI, which commutes with everything except it anti-commutes with this, so it would flip the sign to minus, or from minus to plus. So let's say I have that. All right. So x1 times this is IXI. So the logical x1 information has moved into the second qubit. And so if I measure x2, x3, that would be measuring logical x1 times logical x2, which is, we don't, that's interesting logical information. So we're measuring interesting stuff. That's a bad idea. We don't want to learn anything about the encoded state. So I don't want to measure XX. So let's just try measuring ZZ. Okay, I don't know what's going to happen. Let's see. Let's get some space here. Copy. Paste. Okay, so next what I did is I measure IZZ, Z2, Z3. So the anti-commutes with this, that becomes IZZ. Let's see. It commutes with X1, that seems bad. Okay, we'll leave it. Commutes with Z, logical Z1. Commutes with logical Z2. It doesn't commute with this, so we need to multiply this by the stabilizer, right? So it should be XXX. One thing you can do is you can double check if I've made a mistake. So to do so, you can just check. So each of these should commute. So these commute, these commute, these commute because these commute. These should always anti-commute. They do. These should always anti-commute. They do. And these should commute with these pairwise. So this with this with this. Different logical qubits should commute with each other. So that commutes, yeah. So at least we haven't done something extremely stupid. Satisfies that. All right. So what do we have here? I see. So we're not done, are we? Very close though. I see. So this times this would give us ZIZ, and so Z1 has been copied into Z3. And the second qubit's a problem. Let's get rid of this. Let's get rid of that X. So let's measure. X2. I think. So what happens? Measure X2 or IXI. So IXI. So Z1 I multiplied by the stabilizer before the measurement, so that commutes. Everything else is unchanged. Yeah. All right. So but now if I want, I can multiply this stabilizer times that operator, get XIX. Now we are done. So what I've done is logical X1's unchanged. Yeah. So this is what I've done is I've done a C0 in the opposite direction than what we wanted. But it's okay. So this circuit overall gives us, I don't know, it's equivalent to, I guess, a Hadamard gate there, plus a controlled NOT gate from 3 to 1. So using only measurements, we've been able to implement a gate. Yeah. So the idea here is by introducing an ancilla, we're able to do interesting things. Without the ancilla, we couldn't do anything because any measurement would collapse the information that we're trying to leave unchanged. So a lot of these, so in this architecture, a lot of these qubits are just going to have to be like ancillas that lie around between C0 gates, so that you can implement C0 gates. Another thing here is actually, so in this kind of architecture, the different measurements like x tensor x would be something like, they correspond to loops in this picture. Different loops correspond to different poly measurements. So for example, so 6 choose 2 is, I don't know, 6? Maybe? What's 6 choose 2? 15? 15. Yeah, so 15 is a number of non-trivial, non-identity 2-qubit poly operators. So actually each of these is actually 2 qubits, but they only use one of them. Because they're stupid. No, I don't know why. Yeah. And so actually what they want to do is they actually want to minimize the number of different 2-qubit measurements they make. Because each of these measurements, in a large scale device, these measurements actually have to be done on the chip. So this is a 2-dimensional chip. So in the classical measurement infrastructure or mechanism, it has to be on the same chip as the actual qubits are. And so you kind of try to minimize that as much as possible. So you don't want to use very many measurements. So x tensor x is fine, z tensor z is fine, but you'd rather not do more than that if you can avoid it. I don't know. That's kind of how this architecture works. And it's a fun example of how you can do interesting things with Ancillos and stabilized algebra. Any questions about this?
Do we have a plus states in the second bit?
Where?
Do we have a plus state in the second bit?
Here?
Yeah.
It says so. So if you measure x2, you either get kept plus or kept minus.
Yeah.
But if you force it to be kept plus, then you get kept plus.
Oh.
That's all I'm saying. Yeah, all these measurements are plus or minus. But I just did the plus case for simplicity. You can keep track of the signs if you